Magis Day, everyone! In our lesson on percentage composition by mass, we used a compound's formula to find the mass percent of an element in it and the mass of an element in any size sample of that particular compound. Now, in this lesson, we are going to do the reverse. We will use the masses of elements in a compound to find the formula. And we will look at briefly the relationship between molecular formula and empirical formula. So in this video, our learning target is to determine the empirical formula of a compound based on its percent composition by mass. So, we will be dealing with two types of chemical formulas. The first one is empirical formula, which gives us the simplest whole number ratio of the number of moles of elements in a particular compound. So this is mostly for ionic compounds, where the elements are at their smallest whole number ratios. Now, empirical formulas are derived from mass analysis and will be the basis for molecular formulas. Now, a molecular formula, it shows us the actual number of atoms in each type in a molecule. Okay, so for example, you have C4H10, C6H6. Take note that molecular formula in a way can be reduced into its empirical formula, reducing it to lowest terms. So for example, C6H6 can be just reduced to CH, while C4H10 can be reduced into C2H5. So that's the difference between molecular formula and empirical formula. Now we will be dealing first with empirical formulas. How do we find the empirical formula from the percent composition of a particular compound? So we start with this problem. Okay? A certain compound is composed of 69.58% barium, 6.090% carbon, and 24.32% oxygen. Now what is its empirical formula? So we follow a series of steps in determining the empirical formula of a compound based on its mass percentages. Okay, so the first one is for us to convert the percent compositions into masses, particularly into grams. Okay, we assume that the mass of the compound is 100 grams. Now we are going to convert the masses into moles and find the whole number ratios by dividing the number of moles of each element by the smallest number of moles. And fourth, if it is necessary, if the mole ratios have the decimals 0.333, 0.5, and 0.25, then we will multiply all the ratios with 3, 2, and 4 respectively, so that we will end up with whole numbers, okay, and not decimals. So we will deal first with this problem. So in our problem, we are given the following mass percentages for each compound. Okay, so let's write it down first to be clear. So we have our given, which are 69.58% barium, and then after that one we have 6.090, and this mass percentage belongs to carbon, and the last one is 24.32% oxygen. Right? So given these mass percentages, we are asked to find our empirical formula. So our R, or our required, is our empirical formula, which we can abbreviate as our EF. So for our solution, then the first step is to assume that the total mass of the compound is 100 grams, such that we can convert the percentage signs into grams directly. So let us write down the elements involved. So you have barium, Ba, which is given by 69.58. Now we need not write percent anymore, because as we said, we can convert it directly into grams. So that's grams Ba. Now for carbon, oh, we have 6.090 grams. All right. And for oxygen, we have 24.32 grams of oxygen. So the next thing to do is to convert the following masses into moles. And how do we do that? So based on our knowledge on mole conversions, we can use the molar mass of each particular element uh, to convert the mass in grams into moles. All right. So for example, in here, we will be using the molar mass. Okay. So from grams to moles, we use the molar mass as our conversion factor. Okay, the molar mass of barium is 137.33, and we need to find a way to cancel grams. So 137.33 stays as our denominator so that we will be able to cancel. All right, so the unit here is grams, and on top is 1 mole. Okay, now we can cancel grams here. We can cancel grams. We can get the number of moles of barium, which is, and I like to round this off to the third decimal place so that it will be a precise measurement. So 0.507 moles of barium. Okay. Now the next step or next element is carbon. So the molar mass of carbon is 12.01. So that's 12.01 grams, and on top of it is 1 mole. Now we get to cancel grams of carbon, such that we will end up with 0.507 still moles of carbon. All right. And after that one, we'll have oxygen. We know that oxygen has a molar mass of 16.00 grams per mole. And then we get to cancel grams there. So we end up with 1.52 moles of oxygen. So now that we have the number of moles, so we have now, let's put a label on top. This is our number of moles for each element. Okay, now that we have the number of moles, we can divide everything else with the smallest number of moles. As for this case, the smallest number of moles is 0.507. So we divide everything. Our goal here is to get the smallest whole number ratios. Okay, or the smallest, or the mole ratios, 0.507. Okay, then divide everything with 0.507. Okay, so in here we now have as our result, we have the mole ratios of each particular element. So let's abbreviate that as our MR. Right? So the mole ratio, that's this one was equal to 1. And then for carbon, this also equal to 1. And then for oxygen, you have 152 divided by 0.507, you get 2.99. Okay? Now 2.99 is almost equal already to 3. All right? And so therefore, in the empirical formula, given these percentages we have, okay, we just arrange them according to how the elements are given. 1 mole of barium 1 mole of carbon, so no need to write as a subscript. And then there are 3 moles of oxygen. Okay, so this is now our empirical formula, which is basically our barium, okay, barium carbonate, which is a result of the reaction, okay, between the barium ion and the carbonate ion. And then you notice there that the 2 as a subscript is not reflected anymore. And why is that? We know that barium has a charge of +2 and the carbonate ion has a charge of 2 minus. Okay, so when you crisscross and disregard the sign, then we end up with BaCO3. So this, ladies and gentlemen, is our empirical formula. It's the smallest whole number ratios given our percentages. All right, so that is for our first example. Now let's take another example, this time having ascorbic acid, which we take as vitamin C to boost up our immunity. Alright, so suppose vitamin C contains 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen by mass. Now, what is the empirical formula of ascorbic acid? So again, in here, we can start right away by changing the percent sign into the uh, unit of grams. Okay, so we assume that we have a 100-gram sample. And so therefore, in terms of carbon, there are, let's write C here, there's 40.92 grams of carbon, which we will convert into the moles of carbon. So this is 1 mole of carbon is to 12.01. Alright, so again, this is the molar mass of carbon. 12.01 grams of carbon. Then we get to cancel. So we have, for the number of moles of carbon, 3.407 moles. Right? And then this time for hydrogen, so for H, number of moles of hydrogen, we know that the sample is 4.58%, so that's 4.58 grams of hydrogen, and then we want to convert it into the number of moles of hydrogen. So 1 mole of hydrogen is 1.01 grams of hydrogen. Now we get to cancel grams, so we end up with 4.54 moles of hydrogen. Okay. Some of you may be comfortable, okay, and I also recommend it to really give the elements. So for example, moles of carbon here and moles of hydrogen, so that you will not be confused later on. Now, ascorbic acid is an organic compound, okay, which is basically made up of carbon, hydrogen, and oxygen. So it's a common participating elements for organic compounds. Now this is for oxygen, this is 54.50 grams of O. So we convert it into the number of moles, that's 1 mole is to 16.0 grams of oxygen. So we get to cancel grams, and we end up with 3.406 moles of oxygen. Okay. Right now, what we have are actually the number of moles. So let me write it down because people, the usual mistake for students is that they really round this off already and assume that they are your mole ratios. Now remember that in order to get the mole ratios, you still have to divide everything by the smallest number of moles. All right. As for this case, the smallest number of moles is 3.406. Okay, divide by 3.406. Now, you may have varying values, especially in the atomic masses that we use, but it doesn't matter as long as we end up with the smallest whole number, as long as we end up with the same mole ratios. So this one is also divided by 3.406. All right. So after dividing with the smallest number of moles, we can get our MR for each particular element, right? So as for this case, we have for carbon, okay, we end up with a value of 1.0 or 1, and then for hydrogen, okay, so this is 4.54 divided by 3.406. We actually end up with 1.33, right? And this is where the the fourth rule rather, comes in. Okay, so we need to to do something such that it will be nearest to a whole number as much as possible. Okay, and then we continue first with oxygen, which is also a one, right? So since we have a 1.33 here, okay, if we see the if we see a decimal point of 1.33, then we have to multiply all the mole ratios by 3. Okay, so that remember that 0.33 is just one third of something. So if we multiply it by 3, then we get the nearest whole number that we can. Okay, so we will divide or we will multiply everything else, all the mole ratios, with 3. Okay, so again, this is our fourth rule given above. Okay, so here, if the mole ratios have the decimals 0.33, zero point 0.5, and 0.25, multiply all ratios with 3. Okay, 3 for 0.33, 2 for zero point 0.5, and 4 for 0.25. Okay, to make them whole numbers. So this is what we are doing. Okay, and therefore, our resulting empirical formula is, okay, for carbon, there are 3 moles, so we write the subscript 3. Now, for hydrogen, that's 1.33 times 3. You end up with the value 4, right? So, therefore, hydrogen, okay, in this empirical formula, will be 4 atoms. And then oxygen, 3. Right? So that is C3H4O3. Okay, that's our formula, empirical formula now for ascorbic acid. Sorry. All right. So C3H4O3. Okay, a few moments to reflect or to pause the video if you want. So again, uh, from the mass, we got the mole, and then we got the mole ratios, and then we have now the empirical formula. So a common mnemonic will be from percent to mass, mass to mole, divide by small, and then you get your empirical formula. Again, a percent to mass, mass to mole, divided by small. Okay, so just like what we did to get the mole ratio, and then that's the time you have your EF. All right. Now this time it's your turn to try. So without the guide or without the diagram, you can give empirical formulas of the compounds based on their mass compositions. So I have two items here. You can use any sheet of paper or your notebook perhaps so that you can solve for the empirical formulas of the following sets of elements given their mass percentages. And then I might be asking some of you to show your solutions in class. So pause this video and start answering. So if you got the following answers, K3PO4, that's potassium phosphate, and Na2SiF6, sodium hexafluorosilicate, which is a rodenticide used to kill rodents, then you are correct. Congratulations, and you did well. So that's all for empirical formulas.